Good afternoon, everyone, and welcome to our presentation. I hope you guys are having fun at the summit. I know I am looking forward to the party tonight. You know, kick back and relax for a bit after seeing so many presentations. My name is Adriana Subiri, and I lead the Big SQL development team at IBM. And here with me is Scott Gray, one of our architects in Big SQL. And we're very happy to be here today to share with you the experience that we had in re-engineering Big SQL. For those of you that you are not familiar, we have open source distribution in IBM, Big Insights, and Big SQL is the SQL solution on Hadoop that comes with our distribution. So let me start first by giving you an overview of the agenda and how we're going to structure the talk today. So first, we're going to talk about why we actually re-engineer Big SQL. Big SQL has been in the market for a couple of years, but we made the decision to re-engineer our product. And we're going to go on an overview of what is that we built. And we're going to use that as a framework to be able to discuss what are the challenges that we had in the SQL over Hadoop world in general, and go through how we solved some of the challenges that we had, in particular related to the architecture, the query rewriter, and the optimizer. And we're going to close with a summary of future challenges and things that we're working on today. So why did we decide to re-engineer our product? First of all, I think that if you heard the keynote yesterday, Adrian indicated that SQL right now is one of the hottest things that we have in Hadoop today. And the reason is businesses are looking for a way to move into the world of big data. And SQL is something that they're familiar with. They have a lot of investment. They have people that know SQL. They have applications. They have tools that use SQL. So it would be a very easy transition for them to move into this world of big data. At the same time, when we're thinking about our new Big SQL, we have a trend in the market that is moving away from MapReduce. So we wanted to do something along that as well. Now, SQL users coming from the relational world are expecting the same level of SQL, the same level of functionality that they have in the relational world. So we saw a really good opportunity to actually fill in that gap. And while customers have been in these last few decades developing SQL skills, developing applications and tools, in IBM, we have been developing those engines that they're using. So we have lots of experience building, we have assets, we have code. So why not leverage that and produce a first-class SQL engine on Hadoop? So the result was Big SQL version 3. Our mascot there, we have it right here, our gorilla. An 800-pound gorilla, perfect mascot for IBM. And we decided to replace MapReduce with a modern MPP shared nothing architecture. We also architectured this from the ground up for low latency and high throughput. And we are able to provide the same rich SQL that you have in relational databases. Of course, we also have rich enterprise capabilities. Now, in order for really understand what is the challenges that we had, I really wanted to take one level down in explaining what the product that we produce is about. So at the center of it all, as I mentioned, we have rich SQL, where we need to have this same level of SQL that we have in the relational world. But of course, that is the first thing that you need to have application portability. You want to reuse those applications, those tools, and that's something that we are able to provide with Big SQL. We also want to do that without having to lock customers into proprietary formats. We're very open. You can still use the same formats that you're used to with Parquet or RC file. We actually support them. And of course, you have heard from many people, especially in this conference, about performance. And yes, we perform, and we perform very, very well. And we have a lot of charts and comparisons on how we compare against Hive. But it wasn't really the focus of this talk to talk about these numbers. You can come by our booth. We can talk about it. But we wanted to talk about the technology behind that performance. We have a very powerful query rewriter. We have a cost-based optimizer. And we have optimized the product for throughput. And of course, one of the important things that we like to highlight here is we're not constrained by existing memory. Your data sets, result sets, no matter how big they are, we're not going to fail your query because of that. Another interesting thing that customers have been asking in this area is about federation. A lot of you have data in other systems, Oracle, Teradata, DB2, And one neat feature that we have in Big SQL 3 is the ability to issue a query against Big SQL, and on the same query be able to get data from all those systems. So we have a very good federation capability, which is key for customers that are looking into hybrid data warehouses. And last but not least, we have a lot of enterprise capabilities, like advanced security auditing, workload management, self-tuning memory management, and comprehensive monitoring. So this is what we built, and now Scott is going to walk us through on how we did it and some of the challenges that we faced.
Thanks, Adrian. Am I on? Am I on? I don't think, oh, I am on. Okay, thank you. Thanks, Adriana. So what I'm going to do is I'm going to start out with a discussion, kind of the architectural level of what we built from a physical process and integration standpoint. Then we're going to do yet another transition back to have Adriana talk about kind of the internals on what did we have to change about how we process queries, about how we optimize queries. So first and foremost, as I think Adriana's slide pointed out nicely, we built this because we have the technology, why not leverage it? So Big SQL is derived from one of IBM's shared nothing relational databases. You can probably guess which one. However, it is its own product. And the reason for this is it's sufficiently different. There's features there's features that don't apply to the Hadoop world, so they've been disabled. There's additional features that are specific to the Hadoop world, so they're enabled. So effectively, it's a different product. It's a different product that looks and smells and breathes like other IBM relational database technologies. I was excited to actually put this presentation together with Adriana because I thought, we can put a sales pitch together, but I thought it was way more interesting to talk about the difficulties in building this, because when we first started, I thought, this doesn't look so hard. It's just take a database, teach it how to read these files, and we're off and running. Well, it turned out it was quite a bit harder than that simple description. So I'm going to run through just kind of the high-level challenges that we faced. And first and foremost is just the matter of data placement. So, in your traditional warehouse, the database has fine-grained control over placement and actually takes advantage of it. So if you've got two tables, you're joining them together, they're partitioned on the same key, or if you're joining them together frequently, you choose to partition them on the same key for co-located joins. But of course, in the Hadoop world, no matter where you do the write, the data's everywhere. The data's all over the cluster. So this idea of co-location, more or less, goes out the door. So we needed to teach the database engine how to deal with what we call it scatter partition, randomly partitioned data. And we also had to teach it how to deal with this new type of partitioning, new to the relational world, of the Hive-style partitioned data, where you group your data, say, by directory, and you use your search criteria, your predicates, to eliminate which directories you're going to read. There's also challenges on just the sheer nuts and bolts of it. The database engine typically expects to have its own storage. It has formats for data that are efficient for moving data in and out of memory. Now suddenly we've got to present it with this wide variety of file formats, this wide variety of formats with different capabilities, the ability to take advantage of some can take advantage of information like search predicates or which columns you're querying. And you need to be able to use all of that capability to get the performance out of it. And then finally, just the ability to allow users to continue to plug new and exciting file formats in. Query optimization was another one of the challenges. Statistics on Hadoop, I guess it could be argued that maybe they're not such a relatively new concept, but the general idea is that since there's such a wide variety of file formats, that there hasn't been really a standard in place for how to collect and collect statistics, what statistics are needed, and very frequently there simply are not statistics. You've got files and they're full of data, and that's what we know. And also our database, Hive has recently introduced statistics in a query optimizer, and we'll talk about, we do leverage those, but the database engine itself has the ability to leverage additional statistics. So we needed more, and we'll talk about how we addressed that. And then finally, again, this is not a comprehensive list, of course, but finally is the case of resource management. So this is a topic, we had to keep this presentation short, so we don't go into how we solved this. Come to the booth and we'll talk about it. But we needed to play nice. You know, we're a database engine. We're sitting there on a, we're typically prepared to be on a machine that we own. But now we're living in this world where we have MapReduce jobs, we've got, you know, we've got TES, we've got all sorts of things, HBase, region servers, all sorts of things sharing resources. And how do we deal with it? How do we make sure we don't overload things or we react if other things need resources? So now I'm going to dive a little bit into the architecture side of things. As you would expect of a relational database, we've got, I guess if you kind of mentally set everything aside except the big orange boxes. There's a head node that sits out there, it accepts the client connections, and it's responsible for doing the basic query analysis, the parsing, the optimization, the planning, figuring out how this thing is going to be executed, and then it throws it into the wild. It throws the work out to the underlying worker nodes. And the worker nodes are, of course, the ones responsible for doing all the work, and in the meantime, like any good MPP system, they're streaming data between each other, they're using internal caches to try to do as much in memory as they possibly can. If things won't fit into memory, they're spilling to local disk. So they're all doing their work, they're all working in parallel until they can aggregate the data and bring it back to the head node or the node that the query came in on and send the results back to the client. And this whole process is supported, the interface to the Hadoop world is supported by all the other colored boxes out here. So I'll occasionally use the term F&P. I just thought I should probably at least clarify what it is. It's a fenced mode process. So it's a process that sits alongside the database engine. It does work on behalf of the database engine and communicates via shared memory to make sure that things keep moving quickly. Then we off on the side, I'm going to dive into a few of these boxes in the next few slides, but I will draw your attention to the Hive metastore over there. So just like Impala, just like really a bunch of the rest of the world, we're sharing the Hive metastore. So you create a table in us, we define the table in the Hive metastore, Hive can use it, we can use it, anything using hcatalog can use it, and vice versa. So, you know, as Adriana said, you know, the idea here is to be an open, an efficient platform for working openly with data. SQL isn't always the right answer. Sometimes you need to throw other tools at it. So the scheduler. The scheduler is really kind of is the fundamental, is the heart of this whole thing. Just like Hive, you know, Hive and Impala kind of work side by side, where Hive is the part responsible for planning the query, but doesn't really know how it's run. It's got this kind of separation of duties. And one of the things that, and Impala takes over on the execution side. Similar to that, you know, one of our big goals was to make sure that the database engine is by and large unaware of the fact that it's on Hadoop. Not 100%, there's some concessions and I'll point out some of them. But by and large it is, it's unaware of it. And we make it unaware by offloading certain duties. And one of them is what the scheduler is responsible for. So the scheduler's job is to interface with the Hive metastore when we need the definition of a table, or kind of what we call the extended definition of what it's like, we reach out to Hive to get that definition. It also acts sort of like our job tracker does for MapReduce, that when a query comes in, it's being executed, and we know we need to read a table. What we'll do is we'll take the name of the table and we'll take the predicates, the static predicates that are applied, the search criteria. We'll pass that off to the scheduler. The scheduler will look at the table. Is it partitioned? Okay. Which partitions will apply to it? Now, what splits? You know, what's the data we want to read? And then it'll send a response back to the main engine saying, okay, I want you to go read that table on these 5 nodes. And of course, it's trying to schedule local to the data whenever possible. So at that point, the database engine just knows I've got a query, I need to run it on these 5 nodes, and that's normal, that's work as usual. That's what a relational database does anyway. Well, I actually already said the last bullet, so I'll move on. Other support processes that we have are our I/O engines. So we have 2 I/O engines. One's responsible is our native engine. So for a select number of file formats, really, you know, all the major file formats, we have native interfaces. So we can go, and by native I mean like C, C++ code, so we can go directly after the files for the most efficient, most efficient access to the files. We have a Java I/O engine. So the idea is, if there's a file format that is new and exciting, or one that, maybe you created your own SERDI to process some kind of data proprietary to you, we'll recognize that and ship that work off to the Java I/O engine. And of course, you can join 2 tables. Maybe one's native, one's Java. It doesn't really matter. And so I said, at one point there is a little bit of concession to the database engine's ignorance of the Hadoop world, and that is pushdown. So the database engine is aware of what type of format that it's talking to, what are the capabilities. And so it'll take responsibility of making sure that enough information is pushed down to be able to exploit the capabilities of that storage format. So if you're using Parquet, or if our native I/O engine has the ability to apply predicates right down at the data, so whatever predicates can be applied will be shipped off to the I/O engine for processing, and all the rest will be done as work as usual within the database engine. So what will happen is, as I said, the scheduler says read from these 5 nodes, the database engine tells the 5 nodes to go read and what to filter, and starts getting rows back. And so that's sort of the end of the nuts and bolts of how, how we physically architected it. But that's basic, that's grunt work. No offense to the people that built it, I'm one of them, I was a piece of that. But really where the value lives is the query processing. The value is in this tried and true 20+ year or 20 years worth of expertise in the query optimization, in the query rewrite capabilities, and the planning on how am I going to execute this query. And so that's really where we feel that the main value comes to bear. And actually, so with that, I'm going to hand it back to Adriana because this is her area of expertise. And thanks for listening to me.
Okay. So why is it important to have a query rewrite and a query optimizer? First of all, SQL is a very versatile language, so you can actually write the same query in many different ways. And sometimes when you're writing the query, it might not be the exact thing that would have the best performance when the query is executing. And more with tools and query generators, you have no control over the SQL that is created. In particular, you're going to have lots of redundancy if you're writing queries when you have views, for example. So in the world of big data, making those mistakes can cost you a lot. It could have a lot of penalty. So having the smarts of a query rewriter that can actually do that for you, we think it's an extremely important thing to have. In this example, you can see that's query 17 from TPCH. And we have applied, one of our query rewrites was applied automatically for this one. If you look on the left-hand side, you're going to see that line item table, which is the largest table you have in TPCH, has to be read twice. After the rewrite, we eliminated the correlation, and it's only read once. So that, on its own, with this rewrite, we're able to actually cut the execution time in half. And that's really one of my favorite examples of a very smart rewrite that we have in Big SQL. But we have more than that. We have around 140 rewrites that we were able to leverage. And although most of them were not really impacted by this new Hadoop world, there were some things that we needed to do to take advantage. So column nullability and indexes can really help us when we come to do query rewrites. And as you know, very few Hadoop data sources have indices, and all the columns are implicitly nullable. So we had to come with an alternative on how we can still leverage all these smarts of the query rewriter. And we came up with advisory constraints. So as you can see in the example, we allow, when you are creating these Hadoop tables, to specify the nullability indicators and constraints. And although they're not going to be enforced on the data, they help us when we are actually doing query rewrites. Another important thing, and Scott touched based on that, is the ability to try to eliminate the data as close as possible to the source. So we want to try to push predicates low down into our readers to make sure that only the data that is relevant flows up into the engine. So in this example, you can see that we have 2 local predicates that are being pushed down. Also, in Big SQL, we give you tools to actually understand what's happening with your queries. You're able to explain and see what are the rewrites that are being applied, and what are the access plans, and how we're going to execute your queries, what kind of statistics we use, and what values we use in order to come up with that access plan. And that's the snippet that you have there on the right. Statistics was one of the areas we had to do more work in this particular area. We wanted to make sure that we reuse Hive statistics. We use the analyze table command to collect statistics, but we needed to extend the statistics that were available because our query optimizer and rewriter needed more. Is able to leverage more statistics to make better decisions. So we extended the existing ones with some. For example, we introduced the column group statistics. So if you have a table that has cars and you have make and model, having column statistics between that, it will help us decorrelate those type of queries because we will know that every model only belongs to a particular make. Also, we have automatic determination of which partitions we need to collect statistics for. In Hive, you have to specify which partition you want to collect statistics on. We do that work for you. So you have to only specify you want statistics, and we will determine which partitions we need to get those statistics for. We added table-level versions of some values that are done normally on the partition level. So for mean, max, null count, and others. And we also extended the number of data types that we collect information like maximal value and minimum value and the length of column value in column statistics. Now, all these statistics are still stored in our Hive. We have them as well in our own internal catalogs for easier access, and some of them that obviously are not in Hive today, we had to store them internally, but we are working on restructuring this code to return it to the open source community. Now, one challenge was that not always statistics are available. So some customers might not be running an analyze table. We had to make sure that we don't 100% rely on that to have good performance. So we are able to do statistic fabrication on the fly when we're actually compiling our queries. So we use things like the number of files, the file sizes, the length of the rows, that we know all that information to actually have a good idea of the statistics of those tables. Another big piece that we were able to leverage with not much effort was our costing model. So the optimizer that we have is a cost-based optimizer. And the only really big thing that we had to teach it is to cost the I/O of what we would do for doing a scan directly for Hadoop. That's really the only modification we had to do. In order to do that, we have to introduce some new elements like number of files, size of the files, number of partitions. But other than that, we were able to reuse our cost model as it is today. And there was a really good question on the meetup is what is the cost model take into account? And there are three basic elements, which is the I/O cost, the network cost, and the CPU. Those are the things that we use in order to determine what's the best access plan. Now, one interesting thing is not everything was a challenge. We found some really nice things that Hadoop does for us. In particular, in this case, the optimizer knows us at optimization time, which is the subset of nodes where the data resides. And that allows us to actually make better costing decisions. Again, talking about opportunities. So one of the challenges was that data is not hash partitioned. So for joins, that you need to collocate data in order to perform a join, that is a challenge. But on the other hand, that what we found is that in Hadoop, you have two ways to actually look at the table. One is scatter partition. That means that you only access the data that is local to your node. But also, when you are trying to execute these joins, you can actually look at one of the tables as a replicated table. And you can achieve that in two ways. One is to actually broadcast all the data to all the other nodes for one of the tables, if the table is small enough. But we were able to leverage the HDFS share file system, so that operation does not need to be done in the database engine, but it could be pushed down into the file system. So that allows us to introduce a new parallel join strategy. So in this case, we have to join the table store with daily sales. Of course, the store table is much smaller. So the decision the optimizer makes is to actually try to get the store table where all the daily sales, all the parts of the daily sales tables are on the other nodes. So we have two strategies now instead of one. One is to actually broadcast through the engine that store tables to the others. Of course, you're going to be applying all the predicates as close to the data as possible, but you still broadcast the table through the Big SQL engine. On the right-hand side, we're taking advantage of the HDFS file system, and we are able to do that at the file system level. So everything, so as far as the database engine, what we are doing is reading a table, but the readers will actually access the data that is local to the node and remote as well. Of course, there are cases where we're not that fortunate as to have one of the tables being small, and both tables are huge. And in that case, you have to use a more traditional approach of hashing both tables through on the join key and send it to different nodes to actually process. So this one is still like a standard join strategy we continue to use. Future challenges. The fun of working on Hadoop I learned after working many years in the database world is that it continuously changes by the minute. So it makes the job fun, and it makes us be on our toes to actually continue to find things that we need to improve and we need to work on. So some of the areas we are exploring today in terms of future, more like present challenges, because we're addressing some of them today, is first on the dynamic split allocation. Again, in a relational database world, you have all the system to yourself. Here, you have to share with other workloads, and sometimes it could be that when you're executing your query, suddenly one of the nodes becomes extremely busy. So we need to balance the work and send some of that work to the other nodes. More pushdown. As I said before, the closer to the data that you eliminate, the data that you don't need, the better. So what are the operations that we need to push down? Should we push down more advanced operations like aggregations or joins? That's another very interesting area. Join collocation. Joint collocation will always be a challenge here, being that the data is scattered all over. So we're trying to find better ways to actually collocate this data and be able to make the cost of these joins way cheaper. And we're also exploring SQL MR to make sure that we explicitly perform partition operations. So with that, I would like to mention that we do have a beta on the cloud you can try. I put the link there. You can go, you register, you can play. There is a lab where you can actually take in order to have that experience. And I would like to open it for questions. Oh, yeah. If anyone has a question, we've been asked if you can actually go to the mic.
So for your optimizer, you mentioned that you take into account things like CPU costs and network I/O costs. I'm just wondering, like, how do you determine the cost of those things? Are they based on heuristics, such as the plan and where the data is located, or more about like based on statistics from past executions?
So definitely statistics play a big role. Right. The cost of each particular operation is based in an internal model that we have. In particular, for example, the cost of the I/O, it depends also on the block size that you're reading. In a relational database, it will be a smaller block, and that's one of the things we had to change for the I/O part of the cost, right? So we take all that into account for each of the operators. The optimizer will actually look at hundreds of different combinations of plans in order to make a decision. It's important as well, one of the key things when you're doing something like that based on a cost-based optimizer is what are the filter factors. So after each operator is applied, how many rows you have left, right? To try to understand what's the cost of the next one. And that's where statistics play a very important role, and understanding the cardinalities and the size of things that come, right? And that's where you're gonna see the big differences, especially when you're trying to choose different, for example, join methods, because we support hash join, we support nested loop join, we support merge join, and we support equi-joins and non-equi-joins. So that all is taken into account with the optimizer.
I see, thanks.
No problem.
Hi. So I have a question that, from my understanding, is that the difference between you and the Hive is that you will still query the data in the HDFS, but instead of generally MapReduce job, you will use a different processing engine to answer the question based on the query. So my question is that the MapReduce, first is the massive, very efficient to do the parallelism. Second thing is they have this failover. If the task, if it's failed, they can very smartly pick up, starting a different task to recover that. How did you solve all these problems?
As Scott mentioned, there are things that MapReduce is still better. And that is something that the resiliency is something definitely that Hive does better. but it comes as a cost, right? It comes as a cost with latency. So in that's the one thing that we need to start thinking on how we can address something like that. But in that area, you're right. I mean, you have more resiliency with Hive that you will have with any of the other engines that are moving away from MapReduce.
Actually,
Maybe Scott wants to add to that.
Just add one more question is that if I have built all my the tables or in the existing, because we are the customer use the Big Insight. So if I already define all my tables, partitions in the Hive, will I expect the Big SQL will just work on those metadata?
sure, yeah.
Yeah. Okay. Yes.
Thanks.
No problem.
Hi. In normal, our BMS usually use a lot of indexes in order to speed. What are you doing to compensate this since Hive doesn't provide this capacity?
So, I'm sorry, you want?
No,
Okay.
take it.
So, yeah, first and foremost, our goal here is to work with the existing data sources. So, so we're, to some extent, we're at the mercy and or the advantages of that particular data source. So in terms, so we don't have indexes directly in the meaning that we don't have any storage format of our own. However, certainly, when we're working with certain file formats, they have things that you could quasi call indexes, at the block level. But so what we're going to do is leverage all the capabilities of the underlying storage as much as we possibly can. But yeah, we don't directly, nor can we directly provide an index on external data.
Okay, thanks.
Sure.
Can you comment on the performance of Big SQL compared to other Hadoop SQL like Impala?
Do you want to take that one?
No, I don't want to take
Yeah.
that. Yeah, sure. So we are GAing at the end of this month, and certainly we're working on comparing the performance. I can certainly tell you, but everybody will tell you this, that you're faster than everyone else, right? I think that one of the things we need to work as a community is we need to work on standardizing these benchmarks. We can't keep making all these claims all over the map because people are trying to use the same standards as TPCDS and TPCH, but when you look under the hood, they're not really doing the exact same things that you will do in a benchmark. Either they're using less number of fact tables, they're using a different number of queries, they're actually rewriting the queries. One of the things that is interesting about Big SQL 3 is we're able to run all 99 queries on TPCDS without changing one single line of SQL, right? So, and same thing with all the 22 TPCH, right? And yes, I don't have numbers against Impala yet. We do have the numbers like everyone else against Hive. And we have, of course, like being IBM, our disclaimers are like bigger than the actual charts with the performance numbers. But we have run against, Big Insights has Hive as well. We have done tests against Hive 12. We're working on the Hive 13. And in TPCDS, we were able to run 43 of the Hive queries after some modification. The rest, we really couldn't rewrite them. And we have speed ups that go up to 74x. The average was around 20x. Another, I think, important thing when you are looking at performance numbers, and I work in the DB2 performance team for many years, is people are right now comparing one query using the whole system with a lot of resources. But what happens in the real world when we start having hundreds of users against it? So what are the throughput numbers that you're going to have, right? How are you using your resources, right? I mean, if you cannot run your, and the other thing is the richness of the SQL. Even though performance is something that everybody loves to talk about, if you're going to, in the real world, you're going to have a business to run. If someone comes and says, I'm going to run your queries super fast, but I'm only going to run half of them, the other half, you cannot run them, right? So we have the performance. We absolutely have them. You're going to hear more about it. But we have to work as a community to make this a standard, so we start being much more clear and really transparent with our community on what is that we can and we cannot do. And maybe we need to, I think it's important that we start competing and showing in other areas, not just performance, because it's not only about performance. I think it's about federation, it's about richness of the SQL. But definitely, if you're interested, come by the booth and I'll show you all the performance charts.
Okay.
No problem.
So I missed the beginning of the talk, so you might have already mentioned this, but so currently many of the interactive SQL engines like Impala and Tajo and stuff don't really support nested schemas and complex type like maps and arrays and stuff. Does Big SQL support nested schemas and complex types?
I can cover that one. So yeah, Big SQL 3.0, no, today we don't. That's certainly hot on the roadmap. Ideally, I'm not allowed to officially say it, ideally the next release.
Okay, thanks.
But that's unofficial. Didn't hear it from me. Any other questions? Come on. Okay, well I hope this was useful. I enjoyed it. I thought it was fun.
Yeah, it's great to talk about it. I mean, definitely we're doing everything we can to advance SQL over Hadoop. And again, I think there are many things we can do as a community. I think in particular the performance things needs to get under control. We need to do something.